Mike Mahoney wears many hats at UC Berkeley, including RISELab, the Stats Department, and ICSI. Welcome to the Data Exchange Podcast.
Good to be here, Ben.
And you have been busy pumping out with your collaborators many interesting new research papers. And we'll go through a series of them here systematically. So the first one is the one that won one of the NeurIPS 2020 Best Paper Awards, Improved Guarantees in Multiple Descent Curve for Column Subset Selection and the Nystrom method. So first of all, Mike, what is the column subset selection problem and why is it interesting?
So this was work that grew out of a long line of work, but the most recent work was work Michal Drzezinski and Rajiv Khanna did, and they did a really sort of a great job fleshing this out and answering a lot of questions in a very nice way about this column subset selection problem. So this is a problem that is abstractly sort of a linear algebraic problem. So think I have data and I'm modeling it by a matrix. The matrix has a bunch of columns or rows. I might ask for the best set of columns or the best set of rows.
Best in what sense?
So best in what sense? Before I answer that, let me contrast it with something that seems a little bit similar, but is actually in a lot of ways very different, but provides a baseline for it. So if you're thinking about the data as a matrix, a good baseline is given by essentially the singular value decomposition, the best rank K approximation. And so if you normalize things the right way, this is principal components analysis.
Right.
And least squares, the singular value decomposition underlies least squares, it underlies principal component, it underlies a range of different things. And it's actually a remarkable statement that the best rank K approximation all but gives you the best rank K plus 1, that it's pretty tractable, by which I mean, you might say, does it take n or n log n or n squared or n cubed, but it doesn't take 2 to the n time. And it really has to do with very sort of fundamental aspects of Euclidean spaces that are really important for a wide range of things in data science. And the singular value decomposition is best in a wide range of senses. It's best in terms of reconstruction error. So if I have a data set in front of me and I say, give me the best linear combination of columns, the best rank K subspace, it's best. It's best on spectral norm, on Frobenius norm, on any unitarily invariant norm. If I want statistical guarantees, I might have hypothesize a model. I want the best estimator in some sense. That's a different notion of best, and this still gives you the best. So in a wide range of senses, it's the best. And if you ask the analogous question, not about linear combinations of columns, but about actual columns, and I can tell you why you're interested in that distinction in a minute, but if you ask for the best notion by any of those measures, Frobenius norm, reconstruction error, spectral, anything, it tends to be intractable. And so more or less any notion of best is intractable. And so the thing we looked at was the metrics people in machine learning and data science care about, reconstruction error and things like that. But there's other notions of best, and I think the leading order thing is that they're all intractable, essentially, for the column subset selection problem, where you want actual columns rather than linear combinations of columns.
So you found that in this paper, you found that there's no solution.
Well, so what we showed in this paper.
What kind of result is this, man? It's negative.
Well, no, the reason people are interested in this is because, so there's two things. One is why they're interested in this, and two, what sort of results could you hope to get? So people are interested in actual columns as opposed to linear combinations of columns in a wide range of applications where the columns may mean something. So if you just want better prediction error and precision and recall and trade-off curves for training and test error, what you should probably do is get a deep neural network and give yourself a massive amount of capacity and fiddle with hyperparameters and get something that's widely not interpretable and very unstable and non-robust, but that really nails it and gets the best possible error. Now, aside from a small number of use cases where that's the case, people want to understand what's going on in the analytics pipeline. They want to be able to not just develop model, but validate them and ask if the models make sense in terms of the domain where the data came from, and a range of other things in terms of approximating uncertainty and so on. And in these cases, the prior work on the column subset selection problem was very modest. You could get certain worst case theoretical computer science type worst case guarantees, but they were pretty modest. They were very, very far from what a practical person would want. And so essentially what we showed in this paper was that those worst case guarantees were tight, but they were really corner cases, that for a wide range of problems, they do not appear. And they appear in a very interesting way. And it's analogous to what's received attention in terms of multiple descents, which has to do with qualitatively different phases of learning. So in years ago, in the statistical mechanics of neural networks, people talked about different phases of learning. And it's a different way to approach learning theory than BC theory and traditional statistical learning theory, in which case you have qualitatively different types of phases. And this has been rediscovered in the last few years under the name double descent, where you have the usual bias variance trade-off when you have more data points than parameters. When you have more parameters than data points, you typically ask for the least norm solution. So think of the least norm, more Penrose solution in linear algebra, but that's implemented by stochastic gradient methods, oftentimes for more general problems. And there you get a different bias variance trade-offs. And so what we see is something very analogous. So the reason you see that for generalization is not because generalization is particularly special, but it has to do with volume and capacity. And underlying the best choice of column subset selection are analogous notions of volume. And what we see is an analogous trade-off. And so the worst case bounds manifest themselves, but if you go beyond worst case analysis to ask how this depends on the problem structure, the worst case do exist, but they really are corner cases and they can very easily be regularized away. And for anything but those corner cases, you get much better results.
So in the NeurIPS statement awarding the best paper for this work, they said this paper will have substantial impact in, for example, kernel methods, feature selection, and as you said, double descent behavior of neural networks. So what is the implication to kernel methods and feature selection?
I mean, there's been a lot of work in machine learning in the last 15 years on what's called the Nystrom method. And the Nystrom method is basically the column subset selection problem applied to positive definite matrices. And there's two rather different lines of work. One was work that I'd been involved with, Trineus and Gittins and others. And essentially it took the data as given and asked for, I want to be good relative to that data. And there's a large body of other work by a range of people in machine learning and ICML and NeurIPS communities, where they asked basically statistical type guarantees having to do with risk. And the two approaches really were very different. I mean, Ahmed Alawi and I had a paper about 6 or 7 years ago, which sort of tied the two together in a sense. But it's sort of an oil and water combination when you ask for results on the data in front of you versus inferential type risk guarantees. And so I think there's a lot of work in the area, and I think a lot of the theory doesn't provide a particularly strong guidance to the practice, and it has to do with exactly this issue. And so the techniques underlying this NeurIPS Best Paper Award had to do with determinantal point processes and volume sampling and related techniques that really, I think, will allow a lot of the work in randomized linear algebra to go beyond numerical methods and worst case type guarantees to getting better inferential guarantees. And so, for example, we can understand the implicit regularization in various sort of approximation algorithms for the Nystrom method. And whether it's a Gram matrix or a correlation matrix, you could be working on either data subsampling, either data points or features. Linear algebraically, it doesn't matter. Of course, in terms of how it feeds to the downstream machining pipeline, it makes a big difference.
So it seems like everything comes down always to linear algebra.
Yeah, I mean, that may not be 100% true, but maybe 98% true. There's a few other things, but I've not found so many things that if you really think hard about the linear algebra, you can't get pretty good qualitative insight as to what's going on.
And so this work, Mike, do you think do you think the work in this paper will make its way into practice and libraries at some point?
Yeah, I mean, so we have a project where we're doing trying to implement randomized linear algebra techniques into LAPAC. And so you could ask yourself, what does that even mean? I mean,
yeah,
the trivial thing is just use it as a front end and a random preconditioner and call it traditional method. And that's essentially what blend and pick by Arvam Toledo and LSRN by Meng and I did. But can you introduce it in a more substantial and subtle way? In particular, given that a lot of the machine learning forcing functions are very different than the scientific computing forcing functions that underlie, the motivation for randomized for LAPAC.
So
And I think getting it into libraries like scikit-learn, and I mean, I have a postdoc, Ben Erickson, has Rosetta, who's working on some things related to that. So I think it's slow, but it's slowly working its way into libraries. Yes.
So is it me, or I randomize matrices? It's not a topic that machine learning people normally talk about, right?
So there's two things here. One is random matrices.
Mm-hmm.
One is randomized linear algebra. The random matrices you use in randomized linear algebra tend to be structured, and you make non-asymptotic statements about, and the reason is you want various algorithmic statements. Random matrix theory is a huge area, and it underlies work we've done on that Ben, you and I have talked about before, and that's a large, rich area that grew out of physics and has implications in finance. For random matrices, there has been work in recent years applying those ideas to neural networks. I think there's still a fairly significant theory practice gap, but there is work there. And I think underlying one of the reasons the award-winning paper at NeurIPS is particularly interesting is that to get joint sampling techniques, or to get better volume properties with determinantal point process techniques, which is weed level details, there's very interesting connections with traditional and non-traditional random matrix theory. And so we're hoping to draw strength from those ideas and integrate them much more cleanly into machine learning, because currently they're really used at sort of the hello world level, I think, in machine learning at least.
So the second paper is on adversarially trained deep nets. In particular, that these adversarially trained deep nets transfer better. So transfer learning. So first question here is this, so how did this paper come about, and is adversarial training an active research area?
So this, well, it's an active research area. We took a slightly different perspective on it that I can tell you about. This was a project that came about with two very good Masters of Engineering students working on their capstone project, Francesco Utrera and Evan Kravitz, working with Ben Erickson and Rajiv Khanna. And we were interested in understanding adversarial training, but not just for the training perspective. Training is one question, and how well you do on training and testing curves is of interest. And there's been work on the perspective of adversarial training, and we've worked on that. And if you fold a little bit of adversarial,
so wait, so Mike, so for our listeners, so roughly speaking, what is adversarial training?
So what is adversarial examples more generally, and then I can tell you about the adversarial training. So what the context here is, and there's a bigger context, but if I give you an image, and people want to train to a lot of other things than images, but work with computer vision for just a moment, I can train to images, and it turns out that if I give you new images that are modified imperceptibly, meaning you as the person can't tell the difference, I can have them be classified in completely different ways. And it's called adversarial because I don't add random perturbations. I have to add adversarially constructed perturbations to accomplish that. Now that's
there's a famous example, the pigs can fly example.
Pigs can fly. You turn a stop sign into a yield sign by changing 2 pixels, this sort of thing. Yeah. Now this is, this may or may not be a problem for self-driving car applications, as an actual pain point, but it indicates a fairly substantial model non-robustness, in the sense that if you change a few pixels, and it gets to the question of whether heavily trained and heavily hyperparameter optimized neural networks are really solving ill-posed problems in some sense. If you can have these minor perturbations that are sort of semantically not so meaningful, that create a huge change in the classifier.
So the researchers who are in this area, are they focused on creating the adversarial examples?
So some are, for security or privacy or whatever reasons, want to come up with adversarial examples. They're the attackers. You might say, I want to defend. They're the defenders. They want to come up with defense mechanisms. Not so many people ask the model robustness, non-robustness question that underlies it that I was alluding to. And so the community basically partitions into those camps. The approach we took was a little bit different, where we wanted to understand the model robustness and non-robustness. And ask what would that mean in terms of two important axes that are really rather different, but people sometimes sort of convolve together. One, let me call it generalization, by which I mean machine learning generalization, how well you perform on the data set in front of you. I mean, you hypothesize as unseen data, but really you evaluate it on training, test, holdout data. And the other is, for lack of a better term, let me call it transfer learning, where I really apply it to tomorrow's data, which is different. So if you're not a machine learner, you'd just say, this is how I use models, but it's called transfer learning and machine learning, for lack of a better term. So one, you're basically de facto evaluating it on the data in front of you. And there's a lot of information leakage when you train highly trained, state-of-the-art neural network models. So really, you should think of you're working on the training data. The generalization bounds qua theory are out the door. So one is, some statement about the data in front of you, maybe in a holdout context. The other is I want to apply it to qualitatively different data. And what we found is that if you consider adversarially trained models, by which I mean I'm not attacking or defending, but I'm folding a small number of adversarial examples into the training process. And we'd use this earlier to smooth out energy penalty landscapes to help speed up the training of second order methods. And we've used this in other contexts. But here we're not interested in speeding up training. We're interested in understanding how the generalization versus transfer learning behaves. And roughly what we saw is that you suffer a little bit of loss in call it generalization, meaning on the data in front of me, I might do marginally worse, but I transfer much better. And so I can transfer to new data better. And the intuition is that the adversarial training process robustifies the model and leads you to solving a more well-posed problem. So you're solving, you're working with a more robust model. That it might incur a very slight loss in terms of generalization quality. So if your only metric is I want to be better on training and testing curves, you might not like this. But if you want to be slightly worse and much better on model robustness, this illustrates that the adversarially trained models transfer better.
So give us a sense of how transferable. So in other words, so did you go from images of cars to something completely different? So how much did it transfer over?
Yeah, so we worked, that's a good question, and there's a lot of details, and the paper describes those details, and we have a range of experiences that aren't in the paper applying it to images, but we've also experimented with various sort of perturbations in natural language context, backdoors or non-backdoor type adversarial perturbations. So I think there's nothing surprising here. If you start with very, very coarse images, it's hard to transfer to very, very fine images. If you train to ImageNet and CFAR, you'd get sort of the prediction quality you'd expect. So I think there, if you train to something very toy like MNIST, you're not going to generalize to, transfer to ImageNet. So you get, I think, what you'd expect. We partitioned the data into various classes and showed that, within animal classes and whatnot, so you don't transfer from animals to refrigerators. As you'd expect.
So do you think
it might be a slight lift, but that's not, I think, what most people would be interested in.
It seems like, Mike, adversarial examples and adversarial training should just become standard in some ways, right? So, plus one, as you said, there's it robustifies the model, and two, you might it almost like a preliminary security check anyway, right?
I
there's no
totally
reason why
that.
not to do it. In other words,
I totally agree with that. I think that if you ask any one person, they would totally agree with that. The standards of the area disagree with that. The standards of the area are, I think, that given the quantity and quality of papers and machine learning venues, the conference review mechanisms, et cetera, there's a strong bias towards getting, let's call it state-of-the-art results, which means some epsilon improvement on something previous. And the easiest way to be epsilon better is not to have a new conceptual framework or argue about generalization versus transfer and interpretability and model robustness. It's to have a well-defined number and be better. So a lot of progress in machine learning has been made basically because of contests. And when you have well-defined contests, you have a number that people try and chase, but then of course you may over-optimize to that number. And so I think the flip side of the progress that happens because of contests is that you get this culture that chases these sort of state-of-the-art results. And if you have a broader context, the interpretability, the robustness, that really falls by the wayside, unfortunately.
So I say that adversarial training and examples makes a lot of sense, and and practitioners should do it as a matter of routine. But with that said, so how does someone come up with adversarial examples? So, so are there live? I mean, so I'd like, I guess I pointed this out to you. At least in NLP, people are starting to build libraries to create some of these examples. But as a matter of routine, so how does one come up with
Yeah.
adversarial examples, for instance?
There's two. I can answer that question a couple different ways, and I don't. In computer vision, that's in some sense, a relatively mature area. There's a range of techniques, and the range of techniques boil down to looking at a data point and saying, how much could I perturb this data point in an L2 or L infinity or L1 norm? And so you look at gradients. We had a result a couple of years ago that looked at Hessian information, but you look at gradient information during training, and you ask for the direction that would mess things up the most. And that's visually very compelling. You can use so-called backdoor techniques, which are different types of adversarial setup, but that's a little bit similar. I'm a little bit more familiar with backdoor techniques in NLP than just general adversarial. And there you can ask similar questions. I do training. What happens if I change one word? It's less visually compelling. Whether or not it's as compelling in terms of the use case is a separate question. And I think there's good reasons why you want to be robust at that. In other areas than computer vision and NLP, and I draw those as sort of broad distinctions, but in each area there's different tasks and the details are different. Think of how this is used in scientific applications. I want to come up with a better model for fluid flow. Why? Because I want to understand how the wind goes over the surface of a car if I'm developing a better hydrodynamic models for my car. It depends on the properties of the the car. And there I think you really need to use sort of domain insight. And so
Don't use machine learning, man.
Well, I mean, you can use machine learning, but you need to couple it, I mean, in a more intimate way with understanding of the domain, which usually is more than look at a gradient.
You know the PDE, so just work on the physics, right? So work with physics.
I think what does it mean to have a continuous model? I mean, a continuous neural network model. There's work on in the last couple of years on having to do with ordinary differential equations coupled with machine learning models. But if your training and testing and validation is always in terms of forward error, you may not have all the properties that continuous models might not want, and so you have certain non-robustnesses. And I think this is really tied with the way machine learning researchers and practitioners use optimization, right? They'll convert constrained optimization problems to unconstrained and then use a Lagrange formulation and low precision stochastic gradient methods and violate the constraints. And in computer vision and natural language, that may be fine. If you violate constraints in a physics or engineering application, you might be violating energy conservation, in which case literally your thing's going to blow up. Right. So how you couple, I think you can still use machine learning methods, but you just have to couple them in a more refined way with the data and the domain.
Yeah, I haven't followed I've seen headlines of people solving PDEs and ODEs using machine learning, but I haven't followed exactly how real they are and what the PDE people think about them. What's your sense?
Yeah, I mean, I can give you a hello world. Have me back in 6 months or a year. We'll have more. We have results along those lines. I mean, I think right now there's a range of people working on it, and they're just marking territory and saying, "See, it works here," and there's a bunch of proof of principles to show that it does work. And then there'll be people that come in and say, "Let's get all the details right," and ask more refined questions. And what if you're in this regime of Reynolds number versus that regime? Things might behave in very different ways. So I think right now it's still early days there, but there's some clear proof of principles that it could work and clear points to places where in the methodology, the traditional machine learning methodology is not well suited, but could be if you asked a different question.
I see. So
if you asked a counterfactual question and you want the parameters to mean something, for example, you'd deal with the constrained optimization in a different way.
So then the next paper is kind of an update on something we talked about when I had you in my old podcast, the O'Reilly Data Show, Weight Watcher, and this paper's title is Predicting Trends in the Quality of State-of-the-Art Neural Networks Without Access to Training or Testing Data. I love that title. First question, does the paper live up to the title?
The paper lives up to the title, certainly. I think it's an interesting. I think it's the sort of question. If you and I have asked machine learning theorists and practitioners, and say, I want to predict I have a bunch of models. I want to predict the trends and the quality of state-of-the-art models. And by state-of-the-art, I don't mean toy things. I mean, go out and scrape the web. And with 2 years ago, there was dozens. A year ago, there was hundreds. Now there's 1,000 models.
I'll push your example even further. So predict GPT-4, GPT-5, GPT.
So we have predictions, and currently we've retrodicted and showed how something might behave over time. But the theory underlies this is the heavy-tailed self-regulation theory, and it makes very particular predictions. That doesn't mean a naive interpretation of it would perform well, because the state-of-the-art models are severely undertrained because they're so expensive and so on. I mean, relative to the structure of the model. But this makes predictions about how well norms, how well heavy-tailed parallel exponents would behave intra-model series and across model series. There's not a one-size-fits-all, but you can make trends predict quality. So I think more important than the weed level details of we're better on by this metric or that metric is just the question: can you predict the quality of state-of-the-art models without access to training or testing data? This is related to, but different than predicting generalization. The quality of a model means this model's good. In what sense of the word? Someone that wants to use it says it's good, a practitioner. And so if machine learning here is to really
when you say so, to clarify for our listeners, so what do you mean by predict?
So if I am at a company, I use models. I don't train them. These things are big enough that I don't train them. I use them. I might take them and tweak them a little bit, but I don't know how they were trained. I don't know what knobs they were used, hyperparameters, this, that. You give me a model. First question: did you give me garbage? Is the thing you gave me good, great, mediocre, or terrible? Can you ask that question? So that's the hello world quality, good versus bad, maybe.
Well, I mean, obviously the answer, default answer should be yes, because I chose this model because I saw it in some paper. It did well in that data set.
So what you're saying is that there exists a data set on which it did well.
Yeah. It's not clear it's going to do well on my data set, but at least on that data set, it did well. So.
Right, but I mean, if you're building bridges, there's a set of principles. They don't boil down to Schrodinger's equation and quantum mechanics. They're engineering principles that build up from the underlying physics. Right. And so you might have parameters that say the coefficient of elasticity, and that might be interpretable in terms of bonds and quantum mechanics. But I know for certain metals and certain concretes that the bridge will breathe and expand a little bit. And if you're a good structural engineer, you can go in and you could look at these things and you can say this was built by a good person. They built a good bridge that's going to be robust. You could go in and you could say this was not built by someone. This is not going to do well when there's a medium-sized earthquake. So there exists a set of principles that are consistent with underlying theory, maybe not derived, where you can ask sanity check questions and you can ask good, better, best questions. This bridge is good, but it'll withstand earthquakes at this level. This is better, it'll withstand earthquakes at this level. There doesn't exist analogous theory, and people don't ask analogous questions in machine learning. They don't ask questions to say, given two models, given one model, is it good or bad? Given two models, which is better? And the usual answer is, well, train it, evaluate training and testing error. But unless you think that companies that develop these models are going to release all their data on which they trained the model, then that is off the table. And you can say, well, work with synthetic data. You can say, well, I'm going to release a subset of it. But that rarely would provide good validation. So to go to the extreme case, can you answer this question without any access to training or testing data?
But ultimately, this field is empirical. So yeah, I don't know. But our model is relatively harmless. It's a recommender. I'll just let it go, and then if I can tell within a few hours whether it's good or not. I
mean, that's harmless until you realize that you're recommending things that are racially or genderly very biased, and you hit the front page of the New York Times.
That's true. Yeah. So
Not to
what
mention
you're
that you put it in a user-facing application where someone could die, but that's going to be devastating for a company.
so to make your work concrete, though, so what you're saying is I have a model that I didn't train. So somehow your tool will be able to tell me whether or not this model will do well on my data, or what exactly are you saying?
So roughly it's saying, is it a good model? It's trying to get at principles that determine whether a model is a good model or not. And one principle that may or may not be true, but that people talk about is deeper is better. A different principle is if it's more analogous to the brain, it's better. A different principle is wider is better. I mean, so I think all three of those, if you were to check them out on state-of-the-art models, are false. Never mind, not state-of-the-art. But those are things that are legitimate answers to how would I validate this. We can use
those statements you made are not theorems, in other words.
They're not theorems, but I think you don't build bridges with theorems. You don't fly airplanes with theorems.
Yeah.
Deep learning, in particular, is a very practical business.
Yeah.
Proving theorems, I think, is sort of analogous to trying to derive the best way to build a bridge from Schrodinger's equation. I mean, you want to develop intermediate level, call it surrogate theories or surrogate models, where you can ask questions, because otherwise you prove theorems about incredibly idealized things. You make this a big inductive leap. It's not clear to me that any of the theorems that you derive having to do with the performance of a two-layer anything are predicting the qualitative properties of GPT-3 or 4, for example.
So let's make this concrete. So let's say I get GPT-3, which they, I didn't train it. I may not have access to the source code itself. Maybe I just have the actual model artifact. Can your tool do something with that?
Yeah, so it looks at a range of quantities, and they tend to be they're properties of the data. You have to be careful if you're comparing models within an architecture series, like changing just depth versus changing other knobs. And we're seeing that there's sort of two types of knobs. And I'll mention these two types because even if I'm not involved in the training, I may know that there's GP, what is it? Small, medium, large. There's a small, and so I could say, how does that series progress? Because when you're state of the art, there'll be a 3, there'll be a 4, small, medium, large. And so what you can see is that you would hope that, and the original GPT was released on damaged data, on low quality data, because they said, geez, it's so remarkable we can't release it. So you could ask, given a model trained to good data versus bad data, how would it perform? Given a model trained to small, medium, large, how would it perform? And if you look at spectral statistics norms, which sometimes people prove theorems about in idealized settings, fitted power law exponents, which have to do with how well the model captured correlations over many size scales in the heavy-tailed self-regularization theory, metrics that combine the two, some other things, we can really identify if the model is going to perform well, if there's certain layers that maybe are going to require more optimization or more work, if certain layers may be under-optimized. These sort of questions we can ask and answer.
So at a practical level, what you're saying is if I'm at a company, to go back to your example, someone gives me a model, I can using this tool, I can kind of ask enough questions to say, with some level of confidence, this is a good model.
So the short answer is yes. The long answer is I can't build the Golden Gate Bridge just because I can do something in my backyard. So I suspect that if most people try and take it and work it off the shelf, these are complicated things and it may not perform well. This is not a one-size-fits-all. But the short answer is yes. We have a range of ways where it works. This is an empirical business. We have results. We show how they perform. Every time we see it fail to perform, we look at it, we scrape at it, we look at more details, we learn something a little bit new, and we realize that probably the similar ideas can be applied, but maybe in a slightly different way. So for example, not just the spectral statistics and the heavy tail, but take them apart and look at them separately or something. But yeah, I think the short answer is yes. And so this is the Weight Watcher tool, Charles Martin this is with, and so the Weight Watcher tool, which you can easily download with pip install Weight Watcher.
So where is Weight Watcher, the tool, headed at this point, Mike? So what are you folks going to add to it?
Well, one thing we've been doing recently is trying to get a better understanding of trade-offs between, let's call them architectural parameters and solver parameters. Because in the wake of, after we did the original work on Weight Watcher, there was a contest at NeurIPS last year on looking at a wide range of generalization metrics. And it wasn't even clear that the structure of that contest made sense, in the sense that they were asking to evaluate a very global metric. What counts as reasonable baselines? We observed Simpsons-like paradoxes, where if you look at the entire data set, things behave one way, and if you look at each segment, things behave a different way. And so we're really fine-tuning it to ask some questions along those lines. You could use ideas for better training. We haven't focused on that. We are trying to use it for better analytics and diagnostics and validation. And so understanding things at the fine scale level like that is something we've really put a lot of effort into recently.
So can one think of Weight Watcher as some sort of QA tool?
You could, yeah. Certainly, the way it's being used now, it would be consistent with that.
Yeah. Which brings me to the last topic, and this is a paper I shared with you from MIT, and actually very much in conjunction with what we just talked about on Weight Watcher. So the paper is the computational limits of deep learning, and I actually had the lead author in a previous podcast, Neil Thompson, which I will link to in the episode notes to this post. So what they did is, in certain fields, let's say computer vision, there's enough history that you can start modeling what would it take to improve the error rates even further in some of these well-known computer vision benchmarks. And based on their modeling, they found that it's just getting to the point where it's going to be too expensive, and the environmental impact will be too out of control. So for example, for ImageNet alone, they projected the economic cost of $100 billion to get to their first level of improvement, not the most spectacular level of improvement. So, and then the other thing they found is that hardware alone is not going to solve this problem, right? So there's hardware is kind of a decreasing marginal return. So when you first specialize, you get a lot of improvement, and then you take advantage of that. Then you take advantage of the next thing, and then and so on and so forth. But the marginal returns keep decreasing. And then they close the paper with, well, maybe this opens up the possibility that other schools of machine learning can step up to the plate and make a contribution. So what was your reaction to this paper, Mike, now that you're a complete deep learning convert?
Well, I don't know if I'm a convert. It's an interesting forcing function for the area. Yeah. And I think it comes with pluses and minuses, right? And so if you're honest about both sides, it's interesting technically, but also as, let's call it a sociological experiment, in the sense that along the lines that we were talking about earlier, are you interested in simply training and testing? Or are you interested in other things, the larger pipeline? So I hadn't seen that paper, so thanks for sending that. I took a look at it. I mean, a couple things struck me. One, something that very few papers do, but this one did, is do something like a meta-analysis. So one way to think about the predicting trends in the state of the art neural networks without access to training and testing data paper that you asked me about was we did not develop any models. We went back and looked at hundreds of publicly available pre-trained models. And, when we submitted this paper, reviewer gave us flack to say, why don't you train new models? Actually, one of them just assumed we did. And we didn't. We just looked at publicly available models, which is sort of what this paper did. It wasn't the main point of this. And I think that's common in biomedical analysis in a range of areas. And I think it's sorely lacking in machine learning here. There's so many papers out there doing a meta-analysis like that, I think is valued. The other thing is it pointed out in a semi-quantitative way, in an idealized setting, a linear regression, that if you work with over-constrained versus under-constrained least squares, and if you work with under-constrained, if you put lasso, or if you try and put minimum norm regularization, maybe with SGD, what are the trends you'd expect in terms of trying to capture correlations? And the thing that struck me about the paper, they said the trends are all in the wrong direction along the lines of what you described in terms of how expensive it is. And this is not an incidental thing. This is not something that we can sort of, fix with hardware, this is very fundamental to what these methods are. These methods are function approximators, and that's true abstractly. I mean, people know that, but it's also true just operationally. In terms of the way these things are validated within the machine learning community, they're used to develop models. That's why you evaluate on training and testing error. They're not used to ask counterfactual questions, and they're not used to evaluate uncertainties, and they're not used to do model validation or diagnostics or any of these other things. They're used to train models. And if you're training models, you throw a lot of data at it. There's, n squared, if there's n data, there's n squared correlations, and you want to squeeze every little bit out you can. You can probably squeeze a lot out. You would do very different things if you tried to do model validation, and model validation would give you robustness, but you're doing something very different than the main MO that machine learners are trying to adopt when they use these deep learning algorithms. So I think it really is fundamental to how the methods are being used. And I think to achieve sort of wider adoption, one, in more consumer-facing industrial applications, and two, in scientific applications, you really got to iterate back and ask these validation and robustness questions.
Yeah.
Very different questions, but they're not being served by the ML community currently.
Yeah, you brought up actually a couple of sociological things, right? So the first one is this lack of meta-analysis, and then the second is earlier on you said, adversarial training. If you do that, then you may have lower performance on the benchmark. No one cares if you do adversarial training in that regard, because everyone's just chasing the benchmarks, right?
Yep.
And so, is this something that the community, the machine learning community, is there a certain amount of self-reflection going on as to?
No,
I mean, because everything, all the headlines are still benchmarks, right?
I think there's self-reflection. I mean, I'm talking to you about this. I've thought about this.
Yeah.
I could point to you out a dozen other people who think about this in very deeply, more so than me, right?
Yeah.
I think it's fair to say that for the community, no. The community hasn't gotten to the point where it's really sort of taken this to heart and tried to, in terms of the review process and the hiring process and these questions that are very communal, I don't think it's taken it to heart yet.
By the way, one of the authors, Neil Thompson, did tell me that after their paper published, they did hear from people who reacted positively, particularly the people who are not in deep learning.
Yeah. Well, that makes sense.
Now those schools are starting to get some more attention.
Yeah, and I think it's a sort of paper it's a very valuable paper because it puts out an idea. It's not the sort of paper that would make it into NeurIPS or ICML, the leading machine learning venues, which gets exactly to your point. Has the community taken it to heart, right? It's a sort of paper that would be very hard to get published there, precisely because it's not better on a training or testing error, right? It makes a more sort of broader, more important point.
But at least it seems like it's, I mean, with so much invested in deep learning in these major companies, it would be hard to imagine any sudden switch, right? So at least until someone shows them otherwise.
I think that's certainly the case.
Yeah. And with that, thank you, Mike.
All right, thank you.